Improving analog meter performance. The Pico microcontroller will process an input voltage, scaling it to plus and minus 10 volts. It will simulate a real meter response. PID control the simulation to reduce overshoot. Correct meter linearity. Send the command signal to the analog meter. Here are some things you will need. Test equipment such as a DVM and variable DC power supply are required for calibration. The ADC uses a differential input. The common mode voltage and range is plus and minus 10 volts. The minus input can be grounded. Interested in how the input network works? Visit the GitHub site. A program to read the inputs and drive the meter is needed for calibration. First, we set up I/O pins and define a few variables. The ADC input is averaged and scaled for gain and offset. The result is serial printed so we can adjust these parameters. The voltage is sent to the meter as a differential PWM signal. The meter full scale is adjusted with potentiometer P1. The needle must deflect at least 10 digits for both plus as minus 10 volts in. Apply and record an input voltage that causes the meter to deflect to minus 10, minus 9, minus 8, etc. to plus 10. Enter the data in a spreadsheet. Insert an XY plot. Generate a trendline polynomial. Test the fit by applying meter values minus 10 to plus 10 as inputs to the polynomial. Record the polynomial coefficients. Characterize the meter dynamics. Apply a minus 6 volts to plus 6 volts step or square wave. Measure the time to the peak value. I used an LED to indicate the start. Also measure the peak voltage. Calculate the damped frequency in radians per second. The overshoot is the voltage above a plus 6 volt minus 6 divided by 12. Calculate the damping factor and the natural frequency. A state variable filter is used to simulate the meter dynamic response. Learn more about it on the YouTube video. For now, calculate 2 gains for the filter. We can't easily get the indicator position from the meter, so we use a simulation in the PID control loop to estimate indicator position. The PID control output is sent to the real meter. Our meter PID control program builds on the calibration program. Input I09 is added to turn off PID control when grounded. Additional variables are needed for PID control and linearization. The control loop period is 5 milliseconds. The first part reads and scales the input signal to plus and minus 10 volts. Scaling gain may require an increase due to proportional control. The loss is P divided by P plus 1. In our case, 60 over 61 or 0.984. Only a PD controller was needed for a good response. The differential error signal also has a low-pass filter to reduce noise. The control signal is limited to plus and minus 10 volts. The state variable filter simulates the meter dynamics. Finally, the simulated meter output is printed to serial out. The command signal is sent through the linearizing polynomial, then out to the PWM pins. A plus and minus 6 volt step response with no PID control. The real meter is on the left and the simulated meter on the right. A plus and minus 6 volt step response with PID control. A 1 Hz plus and minus 6 volt sine response without PID control. Note the phase lag and decreased amplitude. A 1 Hz plus and minus 6 volts sine response with PID control. There is good phase and amplitude matching. A 1 Hz plus and minus 6 volts triangle wave response without PID control. A 1 Hz plus and minus 6 volts triangle wave response with PID control. A 1 Hz plus and minus 6 volts square wave response without PID control. A 1 Hz plus and minus 6 volts square wave response with PID control. Thanks for watching.